Well, thanks for the generous introduction. So yes, well, I mean, as Andrew said, I've been working quite a bit on the neural-machine translation or the machine translation in general since I moved to Montreal to do my postdoc. So let me tell you a bit about the current state of the machine translation or the neural-machine translation, and then some of the latest development, and as well as what I think the field is actually moving toward. So let's see if it, oh yeah. So of course, if anybody was asked without actually knowing about how the machine translation is done in practice, then everyone would actually kind of imagine building a system like this, right? So you're going to start with some kind of source text. So this is the typo in their original figure, but you're going to analyze all those words in the sentence, and then given that, you're going to try to get some grammatical structure or the syntactic structure. On top of that, you're going to get the semantics, like the meaning. Eventually, you get the ultimate meaning only thing out of the sentence that has, let's say, stripped of all the linguistical properties from the source language. And then you're trying to generate it following the other direction. Well, unfortunately, it turned out that building all these components are extremely difficult. Just that we just do not have enough ideas on what is the correct syntactic structure, what is the correct semantic structure. And of course, when you're thinking about the interlingua, nobody really knows what that really is. So instead, what has been happening since the late 80s is that it's been all about the statistical approach. That is, we're going to collect as much data as possible. And then those data sets that you collect is going to be a set of parallel sentences. That is, a pair of sentences written in two languages, right? So it kind of started in the 1988 with the team from IBM led by Fred Jelinek. I'm not sure if this is the actual quote, because apparently Fred Jelinek always denied that he actually said that. Oh well, who knows? And then here the recognizer was the actual speech recognizer. So today, what I want to tell you about the machine translation strategy we are going to follow is this same statistical approach. That is, we're going to take the large corpus that has all those, let's say, translation examples, and then we're going to somehow build a machine that's going to read the source sentence and then just spit out the translation one at a time. Okay. So, but before that, of course, we gotta look at some history, right? So knowing the history is pretty important. So interesting thing is that all this machine translation research, if you look at all these different variants of the machine translation research, they are pretty much, let's say, very closely related. And then especially if you look at the neural machine translation, which we think, there is a tendency that we think that that's a new thing. In fact, started as early as the very first statistical machine translation system you can think of. That is the IBM model. Or in 1992, there was a book by Hutchins and Somers. The title was An Introduction to Machine Translation. It's a kind of, let's say, really nice and then well-written book. I highly recommend you to read it, except that it's a very unfortunate book as well in terms of the timing of publication. So they wrote a very, let's say, thorough textbook right before the IBM came up with the statistical approach to the machine translation and kind of, let's say, changed the whole game. So unfortunately, this book is talking all about the rule-based system that kind of got invaded by the IBM statistical machine translation approach. But already in this book, in 1992, they said that the connectionist model, so you can read it as the neural networks, connectionist model to natural language processing is clear enough as a psychologically real model of how humans understand and communicate. Okay, so the second part is kind of, let's say, it's difficult to tell whether that's true or not, right? But at least already the neural net-based translation or the natural language processing was acknowledged as early as in 1992 as a very viable approach. And of course, this is not, these folks are not the only ones who've been thinking about that. Already in 1987, there was the very first international conference on neural nets. And then Bob Allen, who is now a professor in Yonsei University in Korea, wrote a paper showing that you can actually build this kind of neural translation system to do the translation. And then in this paper, he translated from the English to Spanish. And it was followed up by the Chrisman in 1992, so he was at CMU back then, proposing almost identical looking neural net, again to do the translation from English to Spanish. But if you look at the size of the data, so he used a 216 parallel pairs, and then half of them were training set. So he built a training set that consists of the 100 examples. So it's no wonder it really didn't work back then, right? So nowadays, we use the 100 millions of parallel pairs, and then that barely makes our system work, and then he was using 100 pairs. So, and then that's why the entire line of research kind of stopped around 1992. And then when Joshua Bengio wrote a paper in 1994 showing that it is actually impossible in principle to train a recurrent neural net to remember anything long enough, people kind of stopped doing it. But of course, like this, let's say, field of the research is gigantic, right? All over the world, people are working on it. So in 1997, people in Spain decided that, okay, we're going to try it out again. So the two groups independently, well, I heard later on that they were actually having beer when they actually came up with this idea. One group from Alicante and then the other group from Valencia, they proposed to use the very same neural nets for doing the translation again with the Spanish and English. But the unfortunate thing is that it really didn't work still, because the size of the neural nets required for such applications and consequently the learning time was prohibitive back then. It was 1997, so it's like 20 years ago. But now what happened? What happened is that we have more than enough computing powers. We know how to train all those nice recurrent neural nets by changing the architectures. We know we have made many advances in the technology, including the attention mechanisms and then like other things that I'm going to talk about. And then what happened after 20 years is that it has become the mainstream machine translation technology. So Google Translate, if you use it ever, then you see that every single sentence you type in there is going to go through the neural machine translation system or the recurrent neural net to generate until it generates a translation. Microsoft Translator uses a neural machine translation. Facebook has moved on to the neural machine translation a few months ago. Systron, which is the largest machine translation service company in the world, or the, let's say, oldest, they also moved on to a neural machine translation. Even the European Patent Office now provides the patent translation service using the neural machine translation. And Booking.com, let's see. And the Booking.com, I don't know, you probably use the Booking.com quite a lot. At least I use it quite a lot. They use machine translation extremely extensively. And a lot of descriptions and reviews you see, I don't know if you've noticed it or not, they are often automatically translated ones. And then many users don't even realize that they are automatically translated. And then let's say rate of booking or the reservation doesn't really change whether the description was translated or not. So it has become the mainstream thing. And then, like this kind of, let's say, news, whenever I see them, I feel a bit, like frustrated, because I thought when I was writing some proposals in 2013 and 14, I was saying that, okay, this kind of neural machine translation is going to be the big thing for the next, let's say, 10 years. And then we need to do the research for like next 10 years in order to make it really work. And then within like two years, it seems like it's all working, right? And then you probably have tried it yourself, and then it actually does work much better than before. But is that the case? But fortunately, that's not the case, because getting a better single-pair translation system was never our goal. Our goal was to actually go much further. That is, can we do translation in a way that the existing, let's say, phrase-based statistical machine translation system couldn't do at all? Can we do the machine translation in a setting that a lot of machine translation researchers have never thought about in? So our goal was never a better single-pair translation system. And today I'm going to tell you a few things that we have done in order to go beyond a single-pair translation system. So first, let's talk about the character-level multilingual neural machine translation. So this is a very interesting question. What is a sentence? So, like, it depends on, who you ask, but often, let's say, majority of us is going to say that, it's a sequence of words. That's going to be the obvious answer. But, like, if you speak a language that is morphologically very rich or have a lot of compound words, then you may say that, it's actually not a sequence of words, but the sequence of subwords or the morphemes, right? Well, but like at the end of the day, how do you type when you write something or when you read something, right? You actually type one letter at a time. So maybe it's a sequence of sequences of letters. Or actually, is the separation of these sequences of letters like natural? Maybe not. At the end of the day, what do? You just type without thinking, right? So maybe it's just a sequence of characters. But now, if you start thinking in this way, maybe it's just sequence of bits, right? Whatever you type on, let's say, Gmail or, let's say, browser window, that's going to be sent to, let's say, another person's, let's say, mailbox as a sequence of bits. So maybe it's just a sequence of bits. It's kind of confusing. And then so far, much of the machine translation research have focused on the sequence of words and the sequence of subwords because of the issue with the data sparsity. But recently, some people have started working on also a sequence of sequences of letters. Now, these are all good. So this is the paper from 2015, very nice paper. 2016 from Feng Luong and Chris Manning. But the question is, okay, why do we have to work with these, right? That's kind of basic question that everyone should have asked, just that we never really asked, because like it's kind of obvious that the sentence is a sequence of words. But then we decided that if you think about, let's think about how a sentence looks like to a neural net. We should look at that, right? So how sentence looks like to us doesn't really matter to neural net because it's going to look at the sentence in a very different way. And then if you think about how we encode a sentence before we feed it to the neural net, is that we use so-called one-hot encoding, or the one-of k encoding, one-hot vectors, or so on. That is, we're going to build a vocabulary of the unique tokens. Now, tokens can be unique words, unique subwords, unique letters, unique characters, unique bytes, and so on, right? So we're going to build a vocabulary. And then for each token or the symbol in the sentence, we're going to replace that symbol with the integer index from the vocabulary. And then, like this kind of one-of k encoding is a very standard way to encode the integer index. And the very interesting thing is that this encoding is completely priorless, meaning that every single word or the token in the vocabulary is equidistant away from every other word. So, we are not actually telling that the and o should be similar because, like they are both articles, and then, like people make mistake by, replacing it quite a lot, and then, cat and dog, like they must be similar because both of them are mammal, and then, they usually take advantage of humans and so on, right? So we don't really put any kind of things. And what it means is that the neural nets are very much agnostic to the actual underlying symbols and their meanings. It really doesn't know. From the very beginning, we actually never told neural net whether the input is a sequence of words, sequence of subwords, sequence of characters, sequence of bytes, or sequence of whatever. It just receives the one-hot vectors. Now, in that regard, it's kind of, let's say, a moot point to actually talk about what the sentence is, at least from the perspective of neural net, because neural net only sees this sequence of one-hot vectors, regardless of how we encoded it. Then there's a question of, okay, so then what is the easiest way to encode the sentence into this form, right? And one thing for sure is that the encoding a sentence into a sequence of one-hot vectors becomes more difficult if you try to interpret the sentence as a sequence of words or the subwords. And then most of the issues stem from the fact that the morphology is really difficult and then arbitrary. Especially when you look at the morphologically rich languages such as Turkish, Finnish, and so on, the vocabulary easily explodes. And then there will be always a very rare combination of the morphemes that you never see in the training set. And in many cases, you can always generate those new, let's say, morphological variants. So this is the name of one of the new ministry in Korea. So in Korea, we have the tradition that every time there's a change in administration, they're going to rename all the ministries. I don't know why they do that. So they merged two ministries. First one was called Science and Information Ministry in the previous administration. Second one was the Communication and Technology Ministry. And then they combined that, and now they call it Science, Technology, Information, Communication Ministry. And then, of course, these dashes are, like artificially added for, your convenience, right? And then now, like how are we going to handle that kind of infinitely many varying, let's say, morphological variants? And also, it's really difficult to handle misspellings. Especially when we look at the words, especially when we look at the social media, like the Twitter especially, it's, like all we do, like half of the effort we put in writing tweets is on how to tweak the words or the spelling so that everything is going to fit in 140 characters. So we cannot really write could, it's taking up too many characters. So we should write CLD. Or, like something like that. And then also the reviews and blogs is full of misspellings. And then, like those kind of things, generally called user-generated contents, are, like exploding. And then we need to be able to handle that, right? So I told you about the Booking.com's, let's say, use of the neural machine translation. One of the issues they run into is a lot of misspelled things in the reviews. And of course, like and then the issue is that the patterns of the misspelling cannot be captured if you just build a vocabulary, fixed set of vocabulary in advance. On the other hand, if you look at the actual letters directly, we probably could find some kind of pattern. And then why do we even believe that there is such a pattern? Because like when we look at the misspelled words or the let's say intentionally misspelled words, we actually do understand them pretty well, especially on the Twitter, right? And of course, there are some issues with the modeling inefficiency, but I'll skip this part. All right, so it's working now, yes. Maybe I shouldn't skip any of the details in the slide. As soon as I said I'm going to skip one part, then like kind of started breaking down. But now, so we decided to actually try it ourselves. The funny thing is that except for, let's say, a couple of groups in the world, in the history of machine translation research, nobody actually seriously considered doing the translation at the character level, although that is the easier way to go because you don't need any kind of pre-processing or anything, right? The letters are just there. But when it comes to character level modeling with a recurrent neural net, there are a couple, let's say 3 questions that need to be answered first. And then if you read all those let's say language model using the neural net or the papers on that topic, they all talk about the issue of generating or capturing long-term dependencies. So the generate a long coherent sequence by capturing long-term dependencies. And then a lot of papers actually talk about the issue of highly nonlinear orthography and then whether the neural net can capture that. Well, this efficiency is like getting better and better every day. And then the funny thing is that all those papers talk about, give those arguments without actual evidence often. And then we got curious. Right? So is it actually true that people have observed the issue with these issues with let's say, generating a long coherent sequence or the, like neural net not being able to capture highly nonlinear orthography? Or was it that they kind of presumed that they are going to be an issue and then they didn't even try? So we decided to try. So we wanted to answer the first question first. So in order to answer the first question, we took the existing attention-based neural machine translation system and then simply replace the data on the target side to be a sequence of characters. We're not going to give any kind of boundary between words. It's going to be just a purely characters. Let's say blank space is going to be just one blank space character. Let's say all the symbols are going to be, let's say, like the characters as well. And input, we just leave it as the usual, let's say, standard byte pair encoded subword sequence. So there were 2 things we wanted to check. One is that whether a neural machine translation system can generate a long coherent translation at the character level. And second thing was whether this neural net can work with the 2 different levels of abstraction. So when the input is at the sequence of words, can it still work by generating a sequence of characters or vice versa? And then we decided to test it on the 4 different language pairs, English Czech, English German, English Finnish, and English Russian, using the large enough data set from the workshop on statistical machine translation 2015. We evaluated by using a BLUE score, which is kind of, let's say, standard automatic measures. And what we found was that, in fact, the results were comparable to the subword-to-subword translation. That kind of like brings a lot of interesting, let's say, questions about the previous work in the sense that, okay, why did we actually not go into the character level translation from the beginning, because that should have been the first thing we should have tried. Essentially, we've had kind of wrong common sense, and then the common sense was driving us towards something more complicated than that was necessary. And then, we decided, okay, that's good. So we'll go to the fully character level, right? So we're going to go from the sequence of characters to the sequence of characters in the target language. Now, a lot of people told me that, okay, that's not going to work. Actually, a lot of them told us. And then one of the reasons they told us that, it's not going to work is because of the orthography. Like the mapping from the spelling to the meaning is really super arbitrary. Let's think about the example. We're going to start with the word quit. Now, I'm going to simply insert a letter E at the end. I get quiet. I'm going to then swap the last two letters, T and E, into E and T, and then I get quiet. So they are like right next to each other in the input space. But if you think about what these words mean, they are completely separate from each other. So this kind of arbitrariness apparently was considered very bad for, let's say, neural net learning or any kind of statistical modeling. Also, another thing is the issue with the complexity. So, when we use the recurrent neural net, the computational complexity grows linearly with respect to the length of the sequence, right? And if you have the attention mechanism, which tries to find the alignment between the source sequence and the target sequence at every time step in the target sequence, the complexity, in fact, grows quadratically with respect to the length of the sequence. And then as we go from the, let's say, sequence of words to sequence of characters, we do observe, for instance, in the English, on average, let's say, 4-fold increase in the length of the sequence. So when we went from the subword to subword, from the subword to subword to subword to character, it was okay, just a 4-fold, increase on the one side. But when we tried to go to character, it kind of got a bit too, too slow. And then already the Thang Luong and Chris Manning in 2016, they actually tried this character-to-character model with the existing system as it is. And then they said in their paper, they had to wait 3 months for the training to end. Obviously, we were not going to wait 3 months for training one model. So we decided that, okay, we need to come up with an encoding mechanism or the neural net that is able first to capture this kind of arbitrary mapping from the spelling to the meaning and at the same time reduce the complexity. So we came up with this kind of character level encoder heavily inspired by the Yoon Kim's work in 2015 and 16. So first we used a multi-width convolution in order to capture all those local character n-gram patterns. So we're going to have a convolution layer with, let's say, kernel size, for instance, 5 here. And then we do the same convolution with a different, let's say, 4 here, kernel size, let's say, 3 here, and then 5. And then we go up to 8. And then we just concatenate all of them, all the features we get. And we use the max pooling to drastically reduce the length of the sequence. But now we can actually do that because all those important local information has been captured by this multi-width convolution. Once that's done, what we need is a highway network for nonlinear mapping. So the highway network is, you may have heard about the ResNet, is a kind of better version of ResNet, which was proposed slightly before ResNet, except that it wasn't tested on the ImageNet, so everyone forgot about it. But that highway network works really nicely, so we use the highway network, and not using it kind of made it all break down, so we use the highway network. And only on top of that, we ran the recurrent neural net and then do the attention. And this turned out to be an extreme good choice when we tested on, again, 4 different language pairs, going from German to English, Czech to English, Finnish to English, Russian to English. So as you can see here, this character-to-character level model is comparable to the both subword-to-character level model as well as the subword-to-subword level modeling on all 4 language pairs. And when you do the human evaluation, so we use the mechanical Turk to gather the adequacy as well as fluency scores from the actual humans. So after showing them both the reference translation and then generated translation, what we see is that the character-to-character model, level model is comparable or often better, almost always better than the subword-to-character level model. And we see that this kind of character-to-character level model, as we expected, is much more robust to spelling mistakes, and it can handle a very rare actually this compound word in German never actually occurred in the training set. It can handle the rare word very well, and the kind of, let's say, rare morphological variant is fine. And then it can also handle, this is, let's say, my favorite example, where you have some ironic compound word. So it's a compound word that says that the improvement is worsening kind of thing. It's a worsening improvement, so it's very ironic, but the character-to-character level model was able to translate it perfectly because it does some kind of on-the-fly segmentation itself, and then it can cope with a lot of different variants. So further analysis has been conducted by Rico Senrich in University of Edinburgh. So he took the German to English translation task and then built all those, let's say, test cases according to the to test the grammatical properties. Let's see. And then what he found was that the subword to subword level modeling, BP to, let's say, subword to character level modeling, they all have the similar performance, but have the different properties when you look at the actual translations more carefully. For instance, obviously, character level modeling is amazing at transliteration. It kind of learns to do transliteration on its own. But the syntactic properties tend to be captured better with the subword level modeling. So now the question is, how do we essentially combine these two, right? But this is less interesting so far, right? Who cares about whether it's a character level or what? You know, why don't you just use the bits, or why don't you just use the strokes or the pixels, right? But now the nice thing about this going into a more and more raw level of representation, especially in the language, is that a lot more and more languages tend to share a same set of representation. So if you look at all those European languages and even some Slavic languages, they effectively share the same set of alphabets. If you go into, let's say, China, and then, you know, like China has like a lot of languages, they kind of share all the same set of characters or the letters, I don't know, glyphs maybe. So what it means is that now we can train this model to translate across multiple languages at the same time. What do I mean by that is, in order to know that, we need to talk about what the neural translation does. So we start with some kind of sentence, but this sentence becomes a sequence of integers, right? It doesn't really matter whether we start from the sequence of characters, sequence of words, or not. It becomes a sequence of integer indices. It goes into the recurrent neural net. The recurrent neural net is going to give you a sequence of the continuous vectors. And the continuous vectors supposed to capture the regularities underlying the data. All right, good. And the decoder is going to generate the translation purely based on this continuous representation. So the decoder doesn't really care or don't know in which language the source sentence was written in. It only looks at the continuous vector representation that is the output of the encoder. Now then, there is obviously like a very nice natural follow-up question. That is, what if I had another encoder that's going to read a sentence written in another language and map it into the same space? Can this decoder translate from those two languages simultaneously? And the next question would be that, okay, what if I have another decoder that's going to take as input this continuous vector representation and then generate a translation in yet another language? Can we actually do that? At the end of the day, that should be possible, right? Because in this space, there's nothing that indicates us about the actual hard linguistic symbols or the structure. We got some kind of semantic representation there. If you remember at the very beginning, I talked about the, let's say, the gigantic graph that has the interlingual at the top. This is something like interlingual that has stripped off of all the linguistic regularities. So can we actually build a multilingual machine translation system rather than building machine translation system for every single language pair that you want to do translation between? So we decided to actually try it out in 2016 already, together with the Orhan Firat, who's now at Google Translate. And back then, we already were able to train this kind of model that's going to take as input a source sentence written in any of these 6 languages, and then translate once the sentence has been encoded as a sequence of continuous vectors. we translated into any of these 6 languages as well. And then it worked pretty well, in fact. Then we were surprised. But at the same time, like back then, we didn't know about the character level representation working well, so we were working at the subword level, and then we had to have all those encoders, decoders, pretty complicated thing. And now, with this character level modeling, we don't really have to think about it anymore. We are going to encode a sentence as a sequence of alphabets, and then put it into a sequence of one-hot vectors, or the integer indices, regardless of which language the sentence was written in. So we're going to go from any of the German, Czech, Finnish, or Russian. So for the Russian, it's a Cyrillic, but we can always find the one-to-one mapping. So we're going to give the sentence in any of these 4 languages to the network, neural net, without telling the neural net which language is written in. We don't tell it. We're going to just give it the sentence of sequence of alphabets, and then ask the neural net to translate it into English translation. So we just trained it. It's the very same thing. The model, we didn't change a single bit of the model. We just trained the model. And then it turned out it can actually do the translation as well as, or sometimes better, than the single pair translation models. So the blue bars here correspond to single pair translation models. So each blue bar has its own corresponding model. But this orange bar, all 4 of them are sharing one model. We train one model, and then this model can translate from German to English, as well as a model that was trained dedicatedly for the German to English. And then it can translate actually better for Czech to English, especially in the Finnish to English. The gap is actually pretty significant. Russian to English, pretty similar. And then when we did the human evaluation, in terms of fluency, there was a gigantic gain that we could get from this kind of multilingual model. And this is even more favorite example of mine is that so we trained this model, and then we never gave a language identification. What it means is that now we can give any kind of sequence of, let's say, alphabets. So we decided to give it a sentence that has the intra-sentence code switching. That is, we gave a sentence that starts with German, and then suddenly switches to Czech, switch back to German, and then switch to Russian, switch back to German. We wanted to put in Finnish, but the Finnish has a kind of very different structure, and then it was really difficult to fit it in here. But then we just gave this to our trained multilingual character level machine translation system, and it did the translation perfectly, or actually I would even say that it's slightly better than the reference translation. Yes. So what it says is that that continuous vector space that I was talking about really exists, and then it is shared across multiple languages. And then encoder is able to project the input regardless of which language the source sentence was written in into the shared continuous space, and then decoder just decodes out the translation in whatever the language it was trained on. So it was a really nice observation, and then hopefully there will be some, let's say, good outcome, especially on the social media. Because especially if you're not an English native speaker, then you tend to, let's say, mix in a lot of languages when you, let's say, tweet or post it on Facebook and so on. So, and then there are some, let's say, nice cases where we can show that this one works really well. One of the things is can we actually build a system that can handle multiple dialects really well? So this is the map of the Basque region in Spain. So the Basque language has about 12 to 14 different dialects. And the dialect from, let's say, east, if you're from this region of Basque, you won't be able to actually talk to people from this part of Basque in Basque because the dialects just differ too much. But there has to be some kind of let's say, regularities. And then if we train this kind of multilingual translation system on all of these dialects, they all share the same alphabet sets, can we actually do better translation? Because getting the resource for each of the dialects is extremely difficult because some of the dialects, there are just only about 500 people speaking as well. So that was nice. So that was nice in terms of, okay, so we showed that, okay, neural nets can do something that we didn't know that we were able to do with the machine translation. But now, I don't think I have much time, but because we had some hiccups, so I'll just quickly go through what we can go on top of that, right? Are there some, let's say, technical challenges that we can solve? So the first thing is the learning to decode. So although I told you as if it's really easy to do the translation once we train the neural translation system, but unfortunately that's not true. We know how to train a neural translation system really well, but we really have no idea how to find the translation that has the highest probability assigned by the neural translation system that we have trained. Because the state space grows exponentially with respect to the length of the sentence. And then if you think about the, okay, let's see. So that's going to be the exponential with respect to the length of the sentence. So let's say length is about 20 on average for English. And then vocabulary size, if you consider it as a word, it's going to be about million. Now that's the million to the power of 20. That's a gigantic space. And we don't know how to find the solution from the model that we have trained. So that's why we all often go for the some cheap approximate search, but they are often too approximate. So this is the figure. So this y-axis is going to be blue score in that case, negative log likelihood. So in the case of the negative log likelihood, the lower the better. And then the blue one is the cheapest approximate search algorithm we have, that is greedy decoding. And then as soon as we went to the beam search, which is slightly more expensive, or actually quite a bit more expensive, then we see that we get huge gain. But we have some diminishing, let's say, return. And then we are not even sure how far we are from the actual optimal solution there. And then the same thing happens in terms of the blue score as well. So unfortunately, we just don't know how to do this. And then furthermore, we are not even sure if this is what we want to do. So this is what we do. So our model has learned the conditional distribution over all possible translations given a source sentence. And then by decoding or translation, what we are saying is that we are finding a translation that's going to maximize this conditional probability given the source sentence. But is that what we want to do? That's actually not even clear, because the decoding objectives are often not known in advance. Let's say I want to use the machine translation system for real-time conversation. Of course, I want to improve the quality, but also I want to minimize the delay as well. If I have to build a machine translation system or use the machine translation system for, let's say, K-12 students, I want the quality to be high, but also readability to be high as well. So maybe using a more common words is much more desirable. If I want to implement or use this machine translation system for on-device translation, I want to minimize the computational complexity as well. So there are so many decoding objectives that we need to follow, but only thing we know how to do, well, not even that, but only thing we know how approximately we do is doing this. Then that's probably not what we want to do. So what can we do about it? One thing to notice is that the neural net is a forgetting machine. It's all about how to forget everything. Let's say you want to build a deep convolutional neural net that's going to tell you, given an image, whether there's a panda or not. What does it do? It's going to start with an image. First thing it's going to do is to separate out background from foreground, and then throw away the background, right? That's probably the first couple of layers. And then given the foreground, it's going to do the object segmentation, and then throw away all the objects that are not panda, right? And then given the panda, it's going to do the, let's say, torso segmentation, throw away the torso, looking only at the face. And then given that face, it probably can say whether it's panda or not, whether there's a panda or not in the image. So we start from an incredible amount of information at the input, and then ended up with a single bit information, right? 0, no panda, 1, panda. What it means is that inside the neural net, there is an amazing amount of information that are being thrown away. And then the question is, can we actually utilize that to do better? Let's just go back one slide. In this case, how we do the decoding or search is to look at only the input and the output from the neural net. But considering this kind of scenario, can we actually do the better search or decoding by looking inside the neural net while we do the search? So that's the basic idea, except that how do we do that, right? The hidden layers are kind of complicated and very high dimensional. At least on the computer vision community, they have had a lot of efforts in trying to understand what the hidden layers of the deep convolutional neural nets capture, right? So they know that, okay, they capture edges and corners, and then they capture texture, they capture object parts, and then, often entire objects eventually. But in the case of recurrent neural nets and the language, nobody really knows what's going on exactly. I mean, like the OpenAI was like super excited to find the one neuron that was like the, I don't know, sentiment neuron, right? Like, hey, you know, like when it's, let's say, activated, it's positive, you know, when it's not activated, it's negative. And then they wrote like the big fuss out of it. That means that we actually have absolutely no idea, right? How is that even a thing that we should be excited about? We should be actually depressed that that's the only thing that we have actually figured out so far. And then if you look at, I trained a very small recurrent neural net language model, and then gave as the input, there is a storm on its way. And it's 1,000-dimensional. It's a very small recurrent neural net language model. And I tried to make a sense out of these activations. No, it's really difficult, right? So maybe because we are not good with the high-dimensional vectors, so I decided that, okay, I'm going to take all these vectors from multiple sequences, and then I'm going to non-linearly project it into a two-dimensional space. This is the figure here. Still, I couldn't see anything. That's actually the unfortunate thing, because we are just not good with interpreting these, let's say, hidden vectors. If we cannot interpret those hidden vectors, how are we going to build or design a decoding algorithm that's going to exploit the hidden vectors? I guess like most of you have figured out the answer by now, is that we are actually going to use another neural net, right? Because we know that the neural nets are really good with high-dimensional vectors. Why don't we use the neural net to interpret the hidden state for us? To do so, in order to do so, we need to first realize that this kind of recurrent neural nets define an environment or the world on its own. It has its own internal state that evolves, and then it takes as input an action that's going to modify how the world works, right? So it clearly defines the world, and then now on top of this, we can now build an agent that's going to change how the world works, and then how the world works directly influences what kind of translations we get. So we can do the search as if it's just let's say, training an agent in some, let's say, environment defined by the underlying neural net. So it's a very simple thing, right? So its agent is going to observe the input as well as the internal state of the neural net, and then outputs a signal that is going to be the action to the neural net. So that it's going to modify the behavior of the neural net. When I say this, all those deep learning PhD students go really wild, and then they are really happy because they can do something with, I don't know, deep reinforcement learning, not realizing that none of them actually works, especially in this kind of high-dimensional setting. It's extremely high-dimensional environment, right? So we have, let's say, tens of thousands of dimensional observation. Our action is often several thousands of dimensional real vector. And then almost none of the algorithms actually work really easily. But it turned out that we can actually train in this setting to do a lot of interesting stuffs. The first thing is the simultaneous translation, motivated by the simultaneous interpretation. So the simultaneous interpretation was introduced as a part of the Nuremberg trial after the Second World War. And then the goal is to translate on the fly what is being spoken as well as possible with the minimal delay. So the objective is to maximize the quality while minimizing the delay from the completion of the source sentence to the completion of the translation. So what we decided to do was, well, we had to actually first realize that it's impossible to get the data for that. You can get the data, but it's going to be extremely small. It's impossible. So what we did was, all right, let's train usual neural translation system with the consecutive translation examples. Consecutive translation as in the translation was made after looking at the full source sentence. So that we can easily find. So we train the model, we fix it. We're not going to touch the parameters of that, but we only consider this as the environment on which the agent is going to work. This agent is going to look at what's going on inside the neural net or the environment, and then decide at each time point whether to wait for the next source word or to start translating. So this one is going to make a decision by let's say, making it wait for the next word or making it output a translation. And then we can train this with a policy gradient. It's a very still difficult problem. because the observation is, again, several thousand dimensional vector. And then the number of steps or the length of the episode goes up to, let's say, 200. And then if you think about the action space, it's like 2 to the 100. So it's really a difficult problem, except these neural nets are pretty awesome. It does the amazing disentanglement of the features so that this agent doesn't have to do much to extract the features. Features are very well extracted. It's amazing. And then, we just train a model. What we see is that this is the base, let's say, neural machine translation system we trained. And this one is fixed. It does a pretty good translation from German to English. And then these arrows now shows you the decision made by the agent at every time step. That is, we're going to wait all the way here, and then start translate, wait, translate, wait, and then all the way. And then you see that the translation is perfect, while the delay measured by the area under this area under these arrows is substantially smaller. And then we can always control that. So this is going to be the manually designed, so the algorithm I designed to do the simultaneous translation with the neural machine translation system, so where I couldn't really understand how to use the hidden state. And then these are our proposed algorithm, which is going to look at the inside of the neural net and then make the decision. And then you always want to go toward the top left corner, so that is going to have the high quality and then low delay. And then you see that we can always do much better than the manually designed algorithms. And then, in fact, surprisingly, it's actually getting very, very close to the consecutive translation. And then this all done purely using reinforcement learning without any kind of indication on what is the right strategy to do the simultaneous translation. So I'll actually skip this part. This is slightly more technically involved. But you can read the paper. It's on arXiv and was presented at EMNLP. Because I heard that some people are not going to read the paper if it wasn't accepted these days. So I gotta be careful, right? So the last topic, I promise, okay? I promise. But it's really exciting topic, so I just wanted to, to tell you about it. So we call it nonparametric neural machine translation. Let's say, I don't know, how many of you actually train neural net on regular basis? Can you raise your hands? See, okay, now you all know what you do is that you actually ask the neural net to do the compression and pattern matching. That is, you're going to train the neural net using a large enough training data, and then after training is over, you're going to throw away the training set and then deploy the neural net alone, right? And obviously, when you think about it in that way, you see the issue, right? As the data set grows, neural net has to grow together. Because the things that needs to be compressed into the fixed set of the parameters grows, the number of parameters has to grow. And then the issue is that the data is growing at so fast rate, it's almost impossible to even download a new data set these days, right? So now what we want to do is, in fact, this. That is, our neural net is going to have an ability to access the vast amount of knowledge that changes over time. And then this access is going to be available not only during training time, but also during test time. And then how we train neural net is to use the use cases so the neural net learns how to find the necessary information in order to answer whatever the input that was given. So this is what you want to do. In other words, we are somehow getting closer to the combination or the, let's say, merge of the information retrieval and, let's say, machine translation or machine learning or deep learning in general. So as a first step toward that direction, we worked on something called nonparametric neural machine translation. What we do is that we're given a source sentence, we're going to use the, let's say, off-the-shelf retrieval engine to retrieve a similar sentence pairs from the training set. So we carry over the training set together every time. So in the test time, we have the neural net and the training set indexed by a search engine. We use the Apache Lucene. And then once those pairs are retrieved, we store it in the memory network. So-called key value memory network. And every time the neural machine translation system tries to output the target symbol, is going to look at both the source sentence and a set of target symbols from the retrieved translation pairs. By doing this, we kind of relieve the neural net from having to compress the entire training set onto itself and then do the translation, because it does look at both the source and target of the translation pairs retrieved from the training set. And like this, a kind of obvious curve here. If the retrieved pairs are more similar to the source sentence, we get much more gain. If it's not similar, we don't really get any gain. And then this kind of figure, we can get it from, let's say, any of the corpus we try. And then why is it good? So other than the machine learning, let's say, based argument, what we see is the much higher consistency in the style of writing and then the vocabulary choice. So this is the French phrase corresponding to, let's say, precise duration, exact period, like all those things. So it can be translated into any one of those. Baseline model decided to choose precise period this time. But if you change a bit, it's going to change to, let's say, precise duration or whatever the choice, because all of them are valid. But our proposed model, this non-parametric model, because it looks at the retrieved source and translation from the training set, it decides that, okay, the La Presse was translated into exact deadline, and then it has just copied over the exact deadline, giving us a higher consistency in vocabulary choice. So I think this is going to be very interesting, because once we train this model, we can actually continuously increase the size of the training set, right? Like the translation memory or any kind of thing, and then that can be personalized to each of the user, or they can be personalized toward, let's say, certain domain and so on. Obviously, there are some, let's say, issues there. That is that the retrieval is not that great. Simple text matching really never works. So we got to go into the continuous vector representation to deal with, let's say, synonyms and then a lot of paraphrases. And then the idea is, okay, how are we going to incorporate some data beyond text? Can we actually let this search engine search for not only text, but for images, videos, and then once all those different, let's say, data of the modalities were retrieved, can we train this model to use all those knowledge to the translation better? And eventually, we want to use Google instead of the Apache Lucene here, right? So I'll actually have to skip this. I'll actually skip this and then just conclude it. So in the terms of the neural machine translation, some of the future directions include, first, low resource language pair translation. So some people say that, neural machine translation is going to have a difficult time with the low resource language pairs, but I don't think that's actually true. It's going to be better at the low resource language pairs because it can work with the multiple languages. And then low resource language pair is low resource only if you consider the specific language pair. But if you can actually consider it as the general language problem and then pull all the resources from all different languages, in fact, there is no such thing as a low resource language pair. Already, David Chang and his students in Notre Dame have had, let's say, success in making neural translation system doing better than the phrase-based system in the low resource translation pairs. And then there are some other interesting work, like can we use the zero resource? Can we do the zero resource translation using the visual grounding, for instance? So, like, let's say you went to some new country, you don't know the language they are speaking, but you'll be able to actually learn their language eventually because there are other modalities on which you can ground. So like, so what is this? So it's a column. Then, you know that, this is a column, right? So, and then, can we do the distribution matching between two languages without any kind of supervision? Apparently, that actually kind of works. So people are working on it. I believe that there will be some papers out by the end of this year or the beginning of next year. And then how can we do the discourse level translation? Somehow nobody has actually figured out how to do it properly, okay? And then there are a couple of papers saying that the discourse level translation, they have a neural net that actually does the discourse level translation. We did some thorough, let's say, evaluation by downloading all those code bases and then doing the experiments with the same, let's say, environments. They don't really help, unfortunately, not yet. Maybe it's because of the evaluation method. Because, how much, let's say, improvement can we get to start with from the discourse level information is very unclear. And then also, can we now go into the real-time speech translation? I wrote this like earlier this week, and then apparently Google now has that earbud that's going to do the real time, like the translation, Babel fish. I gotta try that out, but like, I'm slightly suspicious. Yes, I gotta try that out. And then this is for my personal purpose. Is that okay? How can we handle the CJK, like the Chinese, Japanese, Korean letters? So this is like Chinese glyphs here. Like this is the Korean letters, and then like all of these, let's say, things. If you look at it, there is some kind of compositional structure. So in the case of Korean, which is the only language I know, like it's always consonant, vowel, and then optional consonant there. It's going to be consonant, vowel, and then this one doesn't have the vowel, consonant, vowel, consonant, consonant, vowel, and so on. So but like the combination kind of leads to almost infinitely many possibilities, and then we don't want to handle that separately or independently. Can we actually do that better? So some people, including the Graham Newbig and CMU, and Xiang Zhang and Yan LeCun, then when you started looking at it from the, okay, what is the right encoding to start with? And then if we believe that this kind of compositional structure is important, can we use the convolutional neural net on the pixel space to capture that? And apparently that actually kind of helps already. So just a few more outside the neural translation, let's say, relevant research directions. One thing to notice is that it's becoming a kind of network of networks that we are building. So if you think about what learning to decode does, is that it's not a single neural net, but we now have a pair of neural nets, right? So the one original network and then decoding networks, and there can be many decoding networks. And then now the decoding networks don't even have to look at only a single network. You can actually use the information from multiple networks. Now, in order to get there, we need to make sure that we know how to train a set of or community of neural nets to talk to each other and then exchange information. And of course, that corresponds to multimodal processing. Some of the networks are going to be specialized for images, some of the networks for language, some of the networks for the, let's say, speech. And then now, how can we combine them seamlessly? So we need to think of the multimodal processing a bit. And eventually, we need to work really hard on the planning and program synthesis type of thing. That is, let's say we have a community of, let's say, thousands of neural nets that are doing all different things, slightly different things. Given a new problem, how do we know which neural nets need to be selected? And then how do we know which neural nets need to be connected to each other in which order? And then we want that to be automated, because manual engineering is going to run into a problem as soon as we have more than thousands of the neural nets in the pool. So yes, this is my final slide. I really promise it's a final slide, yes. So this is what we are still doing, is that there is some word, and then we have the expert who's going to find the problem, build a neural net, and then train it, and then deploy it to the user. But I think we're now going into this kind of, let's say, modular lifelong learning, where we're going to have a neural net per function, not per task. And then they are going to interact with the word in various ways. And really important thing is going to be how to combine all these to solve a higher level cognitive task eventually. And that's it from me. Thank you. If you have any questions, yes.
We have time for questions.
Yes.
Do you think end-to-end will be sufficient?
Oh, so the question is whether end-to-end is going to be sufficient. In this picture, yes. But in this picture, not anymore, in some sense. So one of the issues with the end-to-end learning is that we cannot really know how each of the module is going to be used in the future. So we actually want to be more, we want those networks to be more generic. And then end-to-end learning to any specific, let's say, task in the earlier stage of the learning is going to make it too specialized and then less useful for the future tasks. So I think it's going to be a mix of the end-to-end learning for each of the modules. But on top of that, there will be always the auxiliary learning that happens over the, let's say, life cycle of this entire community. Yes, behind, yes.
So in your memory augmenting model, do you have to make any changes to the data set because the output does not have any words that are coming from the retrieved sentences?
Yes. So the question is whether this kind of model can translate a sentence when the retrieved translation doesn't have the correct word in the correct words, right? But that's the thing, right? That's the difference between, for instance, let's say existing example-based machine translation versus this kind of non-parametric neural machine translation. This decoding part has an option to either select from the retrieved translations or translate it on its own, right? So it's much more powerful. This fusion part is much more powerful. So yes, it can do that. Yes.
So you're just doing a simple addition from both the encoders?
No, it's not too simple. I suggest you to read it. I mean, it's simple enough that it's just one-liner, but still it's not as simple as just adding them up. Yes.
One more. For your character-based models, if you intuitively feels like it won't learn any semantic structure, so will it be useful in QA problems and stuff?
So good question. So I mean, like, of course, whenever I get that kind of question, my answer is, like, I think the semantics is kind of overrated, and I don't think it actually exists. That's usually my answer. But so let's just assume for now that this does capture some regularities, some of which may be considered as semantics, right? And then it's a matter of how well this encoder does a job, not how the input was represented. So yes, so it should be generally applicable. In fact, there have been a couple of papers, for instance, one from the Microsoft recently last year, showing that when you do the Q&A using the knowledge base, character level models do help, especially with the proper nouns, which is kind of understandable, right? Yes.
So you have encoders with respect to different languages, and you're decoding it into one language. So can you combine multiple languages in different language families? Encoders?
Yes. So okay. So the question was, do we have, let's say, multiple encoders, or the one encoder? Can we just combine them, or so on? And then there was a question of the language family. I'll get to that. So, okay, in our paper in 2016 with Yoram Firat, we had separate encoder for each of the source languages, and then separate decoder for each of the target languages. But in our latest work at the character level model, and then also from the work from the Google as well as the Karlsruhe, in those work now we only use a single encoder and decoder for all these languages. And then also the language family doesn't seem to matter actually, because we added Finnish there, right? Finnish is very, very different from all the other languages, and then in fact, if you look here, Finnish is the one where you actually gain most. So this kind of leads to one lesson that I have learned is that a lot of people who told me that a lot of things that I've tried recently are not going to work were the people who are very, very, let's say, linguistically aware. Let's put it like that. And then the thing is that because the linguistics about how we use language, and that's not about how neural nets use language. So some of the intuitions we get sometimes betrays us. So we have to be careful in how we apply our prior knowledge to, let's say, neural net learning. That would be my lesson. Yes. Yeah.
So have you observed any changes when you're using transliteration? Say you have Korean words which are typed out in English and you're translating it. Have you seen that effect?
Oh yeah, I mean that's an interesting thing. So let me see. So in this work, the paper from 2016 NACO. So we trained this model. We didn't put it into the paper, but after training the model for the slides, we decided that let's try to put my name, my first name, as the input, and then try to translate it into multiple languages. We had the 5 languages there, right? And then it does make different, let's say, transliteration depending on which language you are decoding into. And then I can tell you my first name, especially how it's spelled, does not occur in any of the training set. It probably doesn't even occur in the Korean the corpus, because my way of spelling is a bit old, archaic way of doing it. But once I made the passport, I couldn't change. But it was able to do that pretty well. Yes. Yes.
I have a stupid question. No knowledge absolutely about those things. If you take the particular language, let's say English, it goes through your, what do you call that, not encoding,
Continuous vectors.
right, you go through this database.
I mean, yes. Yes and no. Yes and no. No, that was a very good question. In the sense that so there are two reasons for that. One is that what we are learning is not the point-wise translation, deterministic function, but the conditional distribution. So let's say if we do the autoencoding type of thing, if we train it to just reconstruct as it is, it's going to learn the exactly same thing. It's going to learn to do that, but if we train it together with other languages, what it does is it learns the distribution over all possible reconstructions that are going to have a very similar meanings. But now, on top of that, we have the issue of not being able to do the inference. So that makes it really difficult. We don't know how to do that, and then that makes it really difficult whether the model has not put any probability mass on the exact reconstruction, or it has, just that we cannot find it. So we don't have the exact answer to that. But yeah, it does and doesn't do that at the same time, I guess. Yeah. Okay. Well, thank you. Oh, okay. Yes.
I'm sorry. So I think now become you mentioned like the discourse representations as well. So can you just what do you think about the research direction into conditioning? So how to generate language or machine transfer condition of something.
Uh-huh.
The language of something. So
Right.
what would be the research direction you think?
Yeah, that's the question that I want to have answered to myself, but all right. So, but okay. So what I think is, let me see. Oh, maybe I didn't actually put it there. So okay. One direction that people, the community started taking to is that can you do a multimodal translation to start with, right? So the workshop on statistical machine translation, or now the conference on machine translation, started to have a competition track every year on the multimodal translation. That is, okay, given a sentence and a paired image, can you translate better? Now, that's a very basic thing to start with, right? And then, of course, that image is going to be replaced with more of the knowledge, more structured knowledge eventually. And what it says is that that kind of setting is ideal for neural machine translation compared to many of the existing machine translation systems, because when I talked about the continuous vector space, it's not only the sentences that can be embedded there in multiple languages, but also other entities easily. So you can think of it as, okay, so I have a source sentence. I'm going to first embed it into a continuous vector space. And then I'm going to have another mechanism that's going to look at the knowledge, relevant knowledge, let's say retrieve using the information retrieval system, that's going to also embed it into a continuous vector space, and then works as a biasing this vector toward a specific direction. And then once that's done, the decoded translation is going to reflect both the source sentence as well as the relevant knowledge retrieved. So yeah, so how to embed all those things efficiently is going to be a big thing. I don't really have an answer, though, unfortunately. All right. Thank you.